All right, guys, we're getting started. Thank you. Let's focus, please. Thank you. So we're going to move on to the next unit. We do have a quiz on Thursday. The quiz on Thursday will be on regression, which we did on Monday. And it'll be, I already wrote the quiz. It's going to be very straightforward. I'll give you like a couple of tables. You do the regression equation using the calculator. And I did put the video, I think, in Schoology. Let me double check, just to be sure. So you guys can locate it. Nothing really to study for, just more, we're just going to just do it. I think I put it. Actually, I think if you go here, if you go to, I'll put the direct link for the video, but you can locate it if you go to the Unit 2 playlist. I put it under there as well, but I'll make sure it's more obvious to locate. Anyway, okay, limits. So now we're moving on to the calculus portion of this class, and we're going to be spending quite a bit of time on calculus. Guys, quiet, please. So the first thing to talk about are limits. Limits are the foundation of a derivative. A derivative is an instantaneous rate of change. We'll talk about rates of change when we get there later in this unit. But we have to start with, actually, we'll talk about derivatives in the second calculus unit. So not until probably in March sometime. But what is a limit? So a limit is all about approach. It's what a function approaches as x approaches a certain value. That's really the at its core what a limit is. I could go over all this like verbiage, but let's just kind of just get to doing some problems. But one way to think about geometrically is that let's say you have a polygon inside of a circle. Right now you have a triangle, then a square, then a pentagon, hexagon, and so forth, right? What do you notice as I add more sides to the polygons? How does the polygon compare to the circle? They start to look more and more the same, right? So let's say you assume n to be the number of sides of a polygon. So you notice that you see this limit notation here. So LAM is the abbreviated for limit, LAM. N arrow infinity, n's approaching infinity. N will be defined as the number of sides of the polygon. If you add more and more sides, ultimately the perimeter of the polygon starts to match the perimeter of a circle. What do we call the perimeter of a circle? We call that, yeah, it's more special than called circumference, just 2 pi r, by the way. So C stands for circumference. So if I think of the perimeter as a function of n, what does that represent again? The number of sides. If I think the perimeter is that, well, this perimeter function ultimately is going to approach the circumference. Now, will it be exactly the same? No. It'll look awfully close. Like, what if I have a 100-sided polygon? It's kind of crazy, right? Is a 100-sided polygon purely or truly circular? No. But it's pretty darn close, right? To be purely circular, you have to make sure that any point on the circle has an equal distance to its center. That's not quite the case with a polygon, right? Like, for example, these corners are of equal distance to the center, but not the sides, right? They're different values. So we have to be mindful about that. So it's all about approach. Now, notation-wise, what's happening here? So here you have LAM, x, arrow C, f of x equals L. So up above in the quotations is essentially what is a translation in plain English of what this mathematical notation is telling you. So there's going to be a lot of notational fluency that's going to be required for this, right? But I know you guys can do it because you guys have done a lot of function notation. So I'm sure you guys will pick this up pretty quickly. What does it really mean? If you look at the quotation up above, what is a function doing as x gets closer and closer to C? So that's kind of a translation of what's happening in that notation right below. Another way you could look at it too, and you can write this down if you want, you don't have to. But let's say I give you an example of something like this here. LAM, x here. I'm totally making this up. I'm just making this out of the blue. Let's have this here, right? So what does that mean in plain English?
X gets closer to f of x gets closer to 4.
100%. Let me write down exactly what Sean said. As x approaches, I emphasize the word approaches 2, then f of x approaches 4. So that's really what it's doing. That's what it's telling us. So it's all about approach. And we're going to look at that or investigate that in example 1. So example 1, I have a function, rational function, mind you, x squared minus 3x plus 2 over x minus 2, which we'll simplify very nicely in just a moment. and x is approaching 2. Now here's a problem. If I plug in 2 right now into that function, what's going to happen? Not quite. But what numerically what's happening? What does the top equal? What does the bottom equal? As x gets closer and closer to, or sorry, if I plug in 2, what's what I'm going to say? You get 0 to 0, right? So yeah, so if I look at this here, well, if I do straight up right now, I get 4 minus 6 plus 2 is negative 2 plus 2 is 0. 2 minus 2 is also 0. That's kind of a problem, right? So we don't care about what it equals exactly. What we care about is approach. And look at the table. Do you see how x is approaching 2 closely from the left side? As well, excuse me, from the right side? So what we're going to do, we're going to compute what f of x equals for all these different values to pretty much understand what is really happening with the limit. First off, can we simplify it? Is that possible? Okay, how does top factor? Yep. And what's the bottom going to be? X minus 2. So what cancels? So we're stuck with. So the function really is x minus 1. So that's really what I'm plugging into. That's what I'm plugging into. All these x values are being plugged into that expression here. So if I were to do that, fine. I would get 1, 1.001, 1.01, 1.1, 1.25. Over here, I get 0.75, 0.9, 0.99, 0.999. Was it sorry?
Can we not really fill in 2 on it?
Well, we can if you simplify.
You just use it.
Right. So graphically, what's happening now? I can go to Desmos, but in interest of time, I'm just going to just show you the graph. If you're to graph this in Desmos, your graphing calculator, or you should be able to know how to do it by hand now. You'd have a y-intercept here, point here, a hole here. We'll do a few more tick marks. Go back to pink. Here, there. So graph is that actually looks linear, right? It looks linear. But there's a hole. And again, actually, to answer your question, Sean, you actually are correct. It's actually undefined here. You are correct. I shouldn't have put a 1 there. So I kind of messed up the last class. So I'll have to fix that on Thursday. But it's all about approach. So if I were to graph it, actually, I'll put the graph in Desmos just so you guys see it. Let me clear the screen for a moment. So see, if I were to zoom in, it's nice about Desmos. You can navigate more easily than TI-84 calculators. If I get close, what's y getting closer and closer to? Then all of a sudden, uh-oh. Kind of hard to tell. See, it says undefined. Likewise over here, if I go this way, it gets closer and closer to 1. So it's all about approach. I don't care what it equals exactly. All I care is about approach limits. Say, go ahead.
I'm gonna put this.
Mhm. Mhm.
You mean approaching like from when actually lessons
Both. Actually, I'm glad you brought that up. because I'm going to talk about one-side limits in just a moment. But yes, it's all about approaching both sides, and I'll make that more clear later in notes. So that's what's happening numerically, right? And graphically we saw as well. Okay, let's look at another one. We're going to copy this graph again. Actually, it's kind of dumb. I erased it. So let's see if I can get it back. Nice. I don't want to draw it again. You guys can draw it again if you want. Okay. Let's see here. Let's erase also the junk. Okay, let's look at this graph again. Okay. So this is a piecewise function, right? And how to graph piecewise function, we have to follow the conditions set forth in that function. Like the first equation or expression is that rational function, right? It's true for all x values except what? 2. And clearly I can't play with 2 anyway, so forget about it, right? And then there's another expression, right? Or another function, right? For when x equals 2. How am I going to represent that second expression? What do I do? It's the dot that's floating up above, right? Okay. So still, let's find the limit. So I'm going to take the LIM as x arrow 2 of f of x. My f of x is now a piecewise function. What's going to be my limit in this case? It's still the same. Yeah, still the same. Again, we don't care what y equals when x equals 2. Again, it's all about approach. Any questions so far? Okay, seems pretty basic. Okay. Okay, now, Zay, to answer your question, we're going to talk about the different sides. So if the left and right hand limits are different, so let me show you how a left hand limit looks. So left hand limits, we abbreviate as LHL. Right hand limits, I abbreviate as RHL. If those are not the same, then there's no limits. So let me show you what's meant by that. The LHL we write like this. Lim x, I'll use the letter A. RHL I'll write like this. So RHL is again abbreviated for right hand limit, LHL abbreviated for left hand limit. A minus and A plus. So we use these superscripts to designate what side I'm approaching. So let me give you a good example. We'll say this is at 1. Say is that like 2. And say it's at -1. So say this is f of x, right? So if I take the limit as x approaches 1 from the left side, so what would you say that equals? If I get closer and closer to 1 from the left side, it's getting closer to 2, right? Is it equal to exactly? No, but it gets awfully close to 2. I don't care about what it equals. I just want what it approaches. What about the right side? If I approach 1 from the right side, what's that going to equal now? -1, right? And those are not the same. So when this happens, we say there's no limit. Or we say the limit does not exist. And I'll have an abbreviation for that as well. When I say x approaching 1 from the left side, so x is slightly less than 1. So can x be 0.9? Sure. 0.99, sure. 0.9999999, but infinitely close to 1. But it's got to be less than 1. Here, x approaching 1 from the right side, so could be like 1.1 or 1.01 or 1.0000000 like infinitely close to 1, but not exactly 1. And what's happening is that this is getting closer to 2, it's getting closer to -1. They don't meet up. When that happens, then we say there's no limit. Or sometimes we say the limit does not exist. And there's an abbreviation that is done often in calculus classes. We also say the limit is DNE. Same thing, does not exist. And that's going to be the way we're going to express limits that don't exist. We'll just say DNE. So a lot of this is kind of giving you some of the nuts and bolts right now is what we're getting. Yeah, say go ahead.
So the negative, like a negative a plus dots to sigma positive, which side to show that.
Each side. Yeah. So these are called one-sided limits that I just did right now. What we did in the previous page was what we call a two-sided limit. We have to consider both sides. But right now, I'm looking at one-sided limits. So the two-sided limit does not exist. That's actually what I really meant to say. The two-sided limit. Sorry if I didn't make that clear. The two-sided limit won't exist. So if I said find me the limit as x approaches 1 of f of x, I would say DNE because my LHL does not equal to RHL.
But you still, you could say.
I could do that.
As x approaches 1 from.
Sure,
negative.
sure. You always could do that, right? If it's part of the domain. Yeah, 100%. Okay. Before I move on to example 3, I need to talk about the last bullet point here. But any question about this whole definition of a limit? The whole one-sidedness nature of it. Okay, all right. So let me clear. One other thing we need to talk about too, when infinity is happening. So hopefully you guys remember how tangent looks. And by the way, you guys need to be pretty comfortable with these graphs. So this is why we call it precalculus, right? Because we prepare you for calculus. So you gotta remember how these graphs look. So that's the graph of tangent. Is there another feature I need to add to this? Good. Okay. Where are they? Good. Okay, good. And cyclical, so there's more, but I'll just do one cycle. So that's a pi over 2. Now, this is a left-hand limit. Because see the superscript? It's a minus there. So we think about what's y approaching. So y is approaching positive infinity as x gets closer from the left side. So pi over 2 I know is like 1.57 because pi is 3.14. So like maybe 1.55, 1.56, 1.5699999999, whatever, right? As I get closer and closer, you're going to see that's going to shoot up. Like for example, if I were to do this in my calculator, which had to reboot my computer, so give me a sec here. Yeah, it's also good to use the TI-84 to help you understand what's happening here. Oh, finish, right. Let's make sure I'm radio mode. Yep. Do tangent of like 1.56. That gets pretty large, right? Kind of crazy. But if I do tangent pi over 2, it'll give me an error, as it should, because it's 1 over 0, right? Because unit circle, we know what's happening at 90 degrees, right? So when this happens, we could say the limit to infinity. Let me move the graph. Pop to the side. So you could say it's so 1 it's infinity, or you say D and E. Because technically speaking, infinity is not a number. So what does it mean to have a limit? It means there's a limit, like you have a credit card limit, right? Or you have a cash limit, whatever you're spending money on, right? There's no limit, technically speaking, when it's going up forever. Like sky's the limit, right? Just keeps going up to the sky, right? There's no ceiling, there's no floor or basement. So you could say D and E and you'd not be wrong. You could say infinity and still not be wrong either. But I personally don't care whether you say either or. Actually, infinity is kind of good to say that because it means you're telling me you understand what's happening. But if you said D and E, that's totally valid, right? Because that's really true. Because infinity is an abstract idea, right? It's just a number that goes on forever. Okay. Your homework's gonna look like this kind of stuff. Example 3. It's pretty easy, actually. It's not that hard. So that's a left. Sorry, that's a right hand limit. That's a left hand limit for D. That's a right hand limit for E. B, F, and G are two-sided limits because you don't see a superscript. There's no superscript.
So it's a one-sided limit for you, not two.
100% correct. That's correct. So yeah, let's look at the graph and figure it out. So what do you guys think when I'm approaching 0 from the right side? Yeah. Well, let's switch the colors, a bit of contrast. Yeah, 100%, 0. What about the two-side limit? Yeah, still. That's because of that reason. Mhm. What's F of 0 though? Yeah, because remember, limits are not about approach. Limits are all about, sorry, limits are about approach. The F of 0 is just exact, right? What about the one side limit for 2? If I approach 2 from the left side. But how about from the right side? So the two-side limit does not exist. And then what about as x approaches 3? Yep. So for here, you could use direct substitution. That's okay. That's because it's continuous there. Okay. This, by the way, is called a jump discontinuity because you can see the graph kind of jumps, right? This right here we call a point or removable discontinuity. Because you've taken a point off the graph, you've removed it, right? That's what I call it that sometimes. So that's just some terminology as well. And we'll talk more about that when we get to continuity later. But continuity, as you probably could tell, is going to require a few things. The limit has to exist. That limit exists at 3. The point exists at 3. Does the limit equal the point? Yeah. Here, the limit exists. Does the limit equal the value of the point? No. Here, the limit doesn't even exist at all. So you need all those things to happen. You need the limit to exist, you need the point to exist, you need the limit and the point to be the same value. Which it is at 3, but not the other places. Not at 0 and 2. Okay. Questions? Hey, okay. They're doing great. Let's keep moving. Okay, these get interesting. I'm going to show you the graphs of these. When the limit does not exist, the way you show it You can show it numerically, which means you'll do a table. You can show it graphically, which I'll show the graph. Or you show it algebraically, which we'll actually do later in the notes today. So I'm going to give you each of these graphs right now. And then we'll kind of investigate what's happening. Okay, that's a weird one. That's kind of weird. Do those bunch like pretending like a 4-year-old's drawing. Okay. I'll explain in a moment what's happening. So what's happening for the first one? So if you think about it, there's actually a piecewise function. Because what's happening is that if x is positive, right? What's the absolute positive number? Still the same number. And if you have x up above, like say x is like 0.1, wouldn't x and absolute x be identical, right? If x is positive, so you just get 1. If x is greater than 0. Okay. What if x is negative? Like say I have -1 or -2 or -3 or -4, -5. The top is negative, but is the bottom negative? No, it's gonna be its positive counterpart because you're doing an absolute value. So it'll be -1 if x is less than 0. Hence, the LHL does not equal to RHL. And so that's why it would not exist. So I chose to actually do it graphically for each of these to show you how the graphs looks. I think that's better sometimes just to visualize it. But on the College Board AP exam, there are some non-calculator questions, and you will have to know how to do this algebraically, which I'll show you in a moment. For other types, this one you just do it graphically. For type 2, I have a vertical asymptote, right? Or sometimes they call it infinite discontinuity. That's a more formal name of it. Why am I giving it that name, infinite discontinuity? Y has an infinite nature to it, and it's a break in the graph, 100%. So technically speaking, the left-hand limit and right-hand limit are both positive infinity. But it still doesn't really exist because it's not a number exactly, right? So that's another way of saying that limit does not exist.
And when we're doing polynomials, we wrote like the limits when x goes to positive and negative 50.
That's for horizontal asymptotes.
What?
That's for horizontal or end behavior. We're not there yet. That's Thursday. This last one is weird. I don't want to spend too much time on it. It's called an oscillating discontinuity. Why do you think it's going k-wire as you're close to 0? Yeah, if I do like, what if x is like 0.001? That's sine of 1,000, right? Okay, I don't know what that is, but the thing is, what's the period for sine in general? It's 2 pi, right? So it's just there's a lot of weird stuff happening. As x is close to 0, I'm doing a bunch of periods or a bunch of cycles with very, very narrow periods. It's like instantaneous, like boom, boom, boom. It's like it's fast, really fast, really fast, really fast, right? So Yeah, sure. I'll show you in Desmos how it looks. It's crazy. It's absolutely bonkers. Y equals sine 1 over x. Here we go. Okay, you can't see it just yet. There we go. Yeah.
What?
Now, if I zoom out, if I zoom in, and look how narrow my scale is.
Algebraically graph the equation. Solve this problem.
And look at my scale. It's really tiny. Yeah.
If the limit of one x doesn't exist, then not exist.
Yes and no. Let's come back to that later. There are some situations where I can't. I just can't think of it right now. Yeah. Okay, let's move on, guys. Now let's talk about analytical ways of finding limits or algebraic ways. Okay. We got what time? 1:20-ish. I can't read that. Okay, good. Yeah, we're doing great. Okay, I'm just gonna give you the answers and explain why these are the answers. Okay. So think about what each of these three limits are doing. One x approaching 4, the other one's x approaching 2, the second one x also approaching 2. What are the actual functions I'm plugging into or evaluating? 5, x, and x to the 4th power. Well, 5 is a constant, so who cares what x is approaching? Y is always what? 5. So big deal. The limit's 5. Great, whatever. That's just a line with slope of 1 and y-intercept of 0. So guess what? Just plug in 2 in the line, you get 2. There we go. That's a quartic function or polynomial or monomial, whatever you want to call it. X to the 4th power. Plug in 2 times 2 times 2 times 2. 16. There you go. So sometimes you could just do this. If the limit as x approaches a of f of x could just equal f of a. That could happen. And that's assuming we're continuous at x equals a. That's assuming that. Okay. Questions? No? Okay. Next was kind of funny. Don't overthink it. Keep it simple. Don't overthink it. Okay. So if you think about it, if you have f of x and g of x, right? And you have their individual limits. So whatever fx is, that limit called L. Whatever g of x is, that limit's M, right? If you're adding those two functions together and hey, find me the limit of the sum of those functions, guess what? Just add the limits. That's all you gotta do. Or subtract them. Or multiply them. Or multiply the constant by it. Or divide them. Granted, M can't be 0. Or raise it to the power. Great. Assuming S is not 0 in this case. But that's all you do. It's very simple. Now, for example 5, I just use direct substitution. So I have this.
Oh.
Does that make sense? Now, what you could have done also, I'm just going to do it up here, but you guys can write down below. if you so desire, you could have broke this down like this. I wouldn't recommend this because it's really a pain in the ass to do. But you could have done all this. Yeah. I wouldn't recommend that because it's very cumbersome. But yeah, think about it. What's that individual one? 3. What's that individual one? 5. What's that individual one? 13. You do 3 times 5 minus 13 cubed. That's what the problem is really telling me, that you can decompose this into the smaller parts and find those individual limits and then combine through basic arithmetic operations. Like, oh, let's multiply, let's subtract that, whatever. Raise to a power, big deal. But I think this will be a big deal when because we are going to talk about advanced limits probably sometime next week. And we want to make sure that we are present to these properties because we'll have to, make sense of them. But it's very simple. Don't overthink it. Right. Questions? Right. Some other things I want to say. If you have a polynomial, just plug it in. That's it. It's that simple. Because remember, polynomials are continuous, right? If you have a rational function, which is obviously a ratio of 2 polynomials, right? Again, just plug it in. And make sure volume's not 0, of course. Which we actually did have that happening earlier in our first example today. But yeah, just plug it in. So sometimes it turns out substituting x equals c is fine. And you can do that with a lot of functions. So always try substitution first. But there's a warning, which I'll show you in the next page. When you guys are ready. Sorry, so as you're still running, Sebastian. Okay. Okay. So root x. Root x is kind of a funny one. You know, root x looks like this, right? And if I plug in 4, that's 2, because you could just do root 4. This one's gonna be D&E though. And that's because the left-hand limit can't be found. And how come left-hand limit can't be found? Because my domain is x is greater than or equal to 0. So I just can't do left-hand limit for this. Because remember, this is a 2-sided limit, right? If you don't see a superscript, it's 2-sided. So I know what happens on the right side. There's nothing I can say about the left side, right? I can't say anything about it. Now, could I have said this? Let me write this down if you want. As x approaches 0 from the right side of root x, then sure. The RHL is valid. The LHL is not. That's because you don't have a domain for it, right? Because the domain's x is greater than 0. Greater than or equal to 0, not less than 0. So I can't say that, but I can say the RHL is fine. Okay. Now we get to the fun stuff. Any questions about example 6? Right. So how do you do this algebraically? There's a few strategies. So one strategy was to substitute, right? We did that already. Strategy 1, direct substitution. But most of the time, that's not going to work. Like, for example, if I try direct substitution, what happens for this one? I get 4 minus 4 over 2 minus 2. What's that going to be? Yeah, that's not good. That doesn't work for us. So sometimes you can factor and simplify. So let's work it out. What goes away? Now can I directly substitute 2 in for x? Okay. The one thing I'm going to really caution you, I was just going to say it one time, and then I'll nail you on a quiz or test if you don't do this. I'll put in caps for good reason. Every single time until you finally get substitute. So if you did this problem and felt, well, I don't care. Okay, on the AP exam, I just wrote a 2-point problem, you get 1 point. You get 1 point for the right answer, you get nothing for your work. They're that cruel. They mean the graders from AP. Because you have to show them notation, because technically speaking, you're still doing a limit, right? You're still doing what you haven't evaluated. So you actually have to write it until you finally are ready to substitute. So don't get lazy. You gotta do it every time. I know it's a pain in the ass, but you gotta do it. And I will actually, and if you think I'm harsh, just wait till you get Ms. York because she will really nail you hard on this one. So you have to show it. This is actually an easy limit. You wouldn't see a question like this on the AP exam. They'll give you something a little more challenging, but you have to show that notation. Very important. Until you're ready to plug in. Once you plug in, then you don't write it. But does the algebra make sense? If I factored and simplified and plugged in, that made sense. Okay. Because the other two are a little bit more challenging, but they're good problems. And by the way, 0 over 0 is called indeterminate because we can't determine what it is. 0 over 0 could actually equal any number, believe it or not. Because anything times 0 is 0. But when that happens, we have to resort to some other technique like factor simplify or the next two, which I'm going to talk about. So next two. And can you put the game away, David? Yeah, like I could totally see you, dude. All right. Are you playing geography game? Can I play with you after? All right, okay, cool. I'm gonna finish up then. I'm gonna get that. I'm gonna all right. Let's do this next one here. So first check this. Okay, so that's no good, right? So what we're gonna do instead, we're gonna do the conjugate. Now, do you know what the conjugate is? Yeah, you switch the sign of the operation in between, the radical expression. So let me rewrite it. That's called the conjugate. Why do you think I'm doing this? Because right now that x in the bottom is being an annoyance, right? Because it's causing 0 in the bottom. I don't want that. So if I can somehow algebraically manipulate this expression so that I can get x up top, cancel x on the bottom, then I'll be okay. So that's what I'm trying to do here. But you gotta be careful with your algebra because at the top you have two things you have to FOIL. Root x plus 1 minus 1, root x plus 1 plus 1. If you FOIL it, the middle expressions cancel as they should because you're doing a difference of 2 squares when you do a conjugate. So if I work this out, I get the limit as x approaches 0. And if I FOIL, you guys should know that's x plus 1, right? And then you have two other radicals, like negative root x plus 1, positive root x plus 1. I think you guys get the idea of how that cancels, so I don't need to write it out. And the bottom looks like this. What happens with the 1 and negative 1? We cancel out, yeah. So limit. Yeah, it's up.
I think that root x plus 1
You know why? Because I was pitching a perfect game and I messed up today. Thank you for catching that. I was almost perfect. Okay. This is a straight. That's my third straight class. That's why. HP plus. Thank you for catching it. But I would have caught myself because I would realize something went wrong when I plugged in afterwards. Because I know I should not get 0 on the bottom. Okay, what happens to the x's? You cancel these to kind of 1 up top.
Wait, are we gonna have to write lim every single time?
Correct. But well, I only did 3 times. It's okay.
How do you have to do that?
Because yeah, and exactly. Yeah, you tell him, Thomas. The reason why is because this is an operation that we have to evaluate. We're being asked to employ this operation. I haven't employed that operation until I substituted. So you have to show it. That's why.
They're not playing a game. We're locked.
You're locked in.
John, you're doing math on
Good.
This mystery, you should do David's crossword. That's in the heartbeat.
I will.
It's so good.
Like challenging, good.
Sure. It was too challenging for them.
You
They
need to
could
be like a Latin major.
You know
to do
what
it.
paella is?
Was that
You know what a paella is?
paella?
No,
No, paella.
No, paella like the Spanish dish, but
Song of phrase, paella.
is it spelled P-A-E-A-N?
Yeah.
Like I could spell,
He knows
but
that.
no, I know how to spell. No. But spelling was like emphasizing the 80s. Now you guys don't spell because of texting.
How about an unstressed vowel?
Unstressed vowel.
Yep.
So the vowel doesn't feel.
Like a what do you call
So vowel that's not stressed.
Yeah.
So it's a relaxed vowel.
No, it's like an
All right.
like a schwa.
Anyway, guys, let's get back because we're almost done. Guys, please let me finish. Yeah, let's put the golf away, please. Okay. All right. Thanks. Okay. All right. What's happening here? There's a hole in the graph, guys. If I were to graph this, there's a hole in the graph. I'm not sure how it looks exactly, but we probably expect something kind of like this. I don't know exactly how the graph looks, but regardless, there's a hole in the graph. And so that's why we're seeing that happen. Like it's undefined or it's indeterminate in the beginning, but graphically speaking, there is a limit there. Okay, last one. Okay, so what we want to do here is combine fractions. So you have to find the LCD. Because again, if I plug in 0 right now, I have 1/3 minus 1/3 over 0. 0 over 0 is a problem. That's no good. So what's my LCD here? Yeah, x times x plus 3. Darn it. Made another mistake. Oh, man. Okay, it's good. Almost done today. Good thing I don't have a B period. So 3 times x plus 3. So I have my little x on the bottom. I have my expressions up top. So I got to combine them, right? So that's going to equal the lim as x approaches 3 of 3 minus parentheses. And be really careful with this distribution. You could easily make mistakes here. I'm sorry, repeat that again?
The top is limit 50.
Oh, sorry. Okay, my third mistake for today. Just keeping track. All right. By the way, Jack's good. Yes, go ahead. Because I want to change the denominators, get them to be the same. That's why. Right. So we want to be comfortable with our fractions as well. By the way, x by itself, isn't that x over 1? Yep. That's going to be important because when I clean it up, I've run out of space. So I'm going to do it down here. When I clean it up, the top, this is a complex fraction, clearly. I have negative x over 3 parentheses x plus 3. The x's will cancel. Where did I get the 3 from? Oh, because I cleaned it up. I distributed 3 minus x minus 3. Oh, okay. Right, and negative x. Yes. What's going to happen is that x over 1 and the bottom's going to flip. So it's negative x. And see how these will cancel again. Then you could plug in 0. You get negative 1/9. That's that one. Okay, we got one more, and then we're truly done. Thank you for being so patient. Questions on example 9? Okay, I'll keep it up until you guys are. So again, I had to combine the fractions. That was the best approach. One thing you could have done also, I could have done this. I'll just kind of do it off to the side here. I could have actually multiplied both top and bottom by this. Of the complex fraction. And then what happens, I'll do some cancellations with this. It would work itself out eventually, but it's fine the way I did it.
I know we have to write like lim x to 0 every single time.
Yes.
But like, do we have to do we have to show every single little step? Like,
Yeah.
Do we have to show
Yes.
negative x
Yes.
times 1?
Yes. Yes. This is 20 years of calculus teaching. I'm sorry.
But not even.
Yes.
We can't even just divide by
No.
x. We have to show them
Yes.
multiplying by.
And here's the reason why. Okay, I'll stop saying yes. Here's the reason why. When we get to derivatives, we have to use limits to understand the way derivatives work. And we actually have to show that all that work. We have to be very deliberate about that. You'll see when we start getting into it, but we really don't want to cut corners. Because what I will promise this. Once we get deeper into calculus, we don't have to do this all the time. We will eventually get away from this. I promise that. Okay. But in terms of good teaching of calculus, yeah, I have to agree with. We can't do shortcuts. And the reason why I'm so emphatic about that is that I actually would teach it. I was actually kind of not lazy, but I kind of encouraged laziness when I first started teaching. And when my students went out to college and they had to do more advanced calculus techniques, they just got skewered because they didn't quite understand the conceptual aspects of it. So that's why I'm really being picky about it. Yeah. All right. And that was my fault, obviously, because I was a new teacher back then. Okay, so part A is piecewise function. But here's the thing. You can just do direct substitution, right? Like that's going to be easy. So I'm going to substitute into that second one. Because that satisfies that inequality. No, because I already did direct substitution. Once I substitute, I don't have to.
Right.
Correct. You don't need to write it. Once you start substituting, you're done.
Do you have to write direct substitution?
No, I just say this so people know what I'm doing. That's all. No, Dave, I want you to write a whole essay about it.
Well, I don't know.
No, just,
Oh my God. That is plenty.
yeah.
Not a-
I'm teasing. I'm teasing hard. Sorry. Okay. For part B, however, we'll need to do the left-hand limit and the right-hand limit. All right. So I'm going to do this limit.
For a downfall. That cock like Minecraft.
Was it Minecraft? What was it? What was it? Oh. So the left hand limit's gonna be this. The right hand limit's gonna be this. Those don't equal each other. Correct. So that's how you show that. Okay. Good. Wow. Got this all done before 125. Awesome. Okay. But this is good because the other lessons will be shorter. But I need to make sure you guys got a lot of the foundational stuff today. That was important. I want to make sure that happened. Homework will be the first 2 pages. We'll say handout A, 1 through 5. I'll put in school G. That's it. Jackson, go ahead.
Go to the bottom.